So looking at the systems today, pneumatic ECS and pressurization. These are primarily covered in ATA's Chapter 21. That's your ECS and pressurization stuff. Chapter 36, ATA Chapter 36 covers your pneumatic information. And this is, we're looking at the airframe side of things. There's also air related to the engine, as we'll see in a second here. So pneumatic bleed air can actually be covered in two chapters. ATA 36 is known as airframe bleed air or customer bleed air. Okay, it's going to be used by customer systems, other systems on the aircraft. Chapter 75 is engine bleed air. So things like engine control bleed air, but it can also sometimes include some of the bleed air equipment that feeds into the system, into the customer bleed air, just the items that would be physically located on the engine. So sometimes if you're looking for a pneumatic system valve, for instance, and it is right on the engine, say it's a shutoff valve right on the engine, it might be in 36, it might be in 75. Okay. If it's a valve, if it's like you've seen in turbines class, we looked at like the 3.5 valves, and those that are used for engine control, those are pretty much going to be in 75. But sometimes these pneumatic supply ones can be in one of two, depending on whether it's essentially considered, is it considered more of an aircraft part, airframe part, or is it considered more of an engine part? Environmental control systems, including heat, air conditioning, and pressurization, are all contained in Chapter 21. And that is, again, ECS, known collectively as the environmental control system. So when you put these all together, the bleed air supply and the ECS, it's the air management system. Okay? And that's a term you'll see some aircraft manufacturers use that term, some don't. But it's a very high level kind of catch-all. And so if we look at what that is in the airplane, you see something that looks like this. So, laid out inside the aircraft, you've got your engine supplying air. You've got, any idea why there's an air duct way back here? What's back here? What? Outflow valve are these two little circles right here. Any idea what this duct work would be going all the way back? What's in the tail? The APU, right? That's the APU can be supplying bleed air back in the tail there. So our supplies, three supplies, left and right engine, APU. And then the duct work that runs around. Pressure stuff going to the air conditioning system, running the air cycle machines. Some of it's low pressure air, like all these ducts kind of coming up the sides of the fuselage. Those are just distribution ducts, right? We're going to put that air in various parts of the fuselage. We're going to run air up to the windshield area and the control cabin, cargo compartment, all those different various areas. And then there's also things like water tank pressurization. That's so water comes out of the tap in the bathroom when you go to wash your hands. It can also run lavatory, some like vacuum. It can provide, using a Venturi, it can provide vacuum to suck things out of the toilet. You flush the toilet, and it sucks the stuff away. If it uses that type of a vacuum toilet system. And then other parts are like avionics compartment ventilation, keeping the various computers and equipment cool and things like that. So looking at kind of the pylon area, or the engine area, the airframe pneumatic system, you can see, on our engine, we're typically going to have a section of ductwork. We're going to connect to one or two spots on the engine. Often there's a pre-cooler on the engine because that air coming off of there is too hot even to do anything on the aircraft. So we're going to pre-cool it a little bit before it even goes up into the pylon area or through the pylon area. APU has its little pull off there, typically a single pressure source on the APU, and then out to the various systems. So the division point, if we want to look at, is it ATA 36 or is it ATA 75, is typically what's called the pylon shutoff valve, pylon firewall shutoff valve, or the SPAR shutoff valve. And what this is if any kind of engine, whether it's an engine, our turbofan engine, or our APU, our little auxiliary power unit engine, those have to be encased in something called a fire zone. So they're going to have some kind of they're going to have firewalls and other enclosures, typically made of either steel or titanium, that fully enclose them. So if there is a fire in that area, because we've got fuel in that area, we've got an ignition source in that area, we've got air in those areas. If there's a fire in that area, we need to be able to isolate it from the rest of the aircraft. And part of that isolation is wherever the different the connections run through the firewall, we want to be able to also close those off to seal that firewall. So your bleed air duct, that shutoff valve, is going to be right there at that firewall, 9 times out of 10. Okay. You also have things like hydraulic shutoff valves and fuel shutoff valves and everything else in order to isolate that. But again, we'll talk about that with fire protection systems. But in regards to this, that also is a convenient spot and serves as that dividing point between whether it's an airframe pneumatic system or the engine pneumatic system for most aircraft. Okay. You can look at it from a schematic diagram standpoint as well. And here you can see the areas in the boxes. Here's our engines on the left. The areas in the boxes are considered engine pneumatic system. And the areas to the right here, this manifold and the various items, that is the airframe bleed air system. Okay. And in this case, there's the firewall is inside the box, kind of. And this shutoff valve here is essentially that firewall valve. Okay. Now, they put it on this particular aircraft, it happens to be upstream of the air that flows to the starter. And again, that's so you can get air back to the starter. Okay. If you look at it from a control standpoint and an indication standpoint, these schematics on the right coincide with the ICAS display we see here and the control panel we see here. And so you'll see this, this is your most modern aircraft would look like this. Older airplanes are going to be, steam gauges and whatnot, analog gauges. But you can see the shutoff valves illustrated next to each engine. The shutoff valves next to each engine are controlled by a bleed switch on the left and right bottom corners of the control panel. They're laid out in the same manner. APU, that has a shutoff valve as well. You can see there's a bleed shutoff valve for the APU. Okay. Now, most of the time, these, on something like this is out of the Embraer 175. Most of the time on something like this, as modern as this is, these are going to be automatically controlled for the most part. These buttons are more of an override system. Older airplanes, you have to manually control. When we ran the Paxton 727, you had to manually open the cross-flow valves, and you had to manually turn everything on and off, right? Newer airplanes like this, often they're left in automatic, in an automatic mode, and based on what air sources are running, the computer that manages this will open and close these various shutoff valves. These isolation valves, you can see it's called a cross bleed valve or an isolation valve here in the middle. And then air flows up to the pack for environmental control. Those each have a switch here as well. And then we've got temp control up top. Okay. But, all of this normally is managed automatically on these newer aircraft until something goes wrong or something doesn't work how intended, and then the crew does have the ability to override. Now, these aren't the only switches that are going to necessarily control these valves. As I mentioned, they also serve as a divider point and a seal in case of like a fire. So if there was an engine fire and you had to arm the fire system, we've seen ones where you pull the T handles or where you push an arm button, that also will close these valves. Okay, so there's more than one control per se. But those other controls that are used to activate them, for those emergency situations. That way, if a crew has a fire And the big reason these close for a fire is you don't want to be pumping smoke up into the aircraft through the ventilation system. Right? It's less of a supply to the fire. You know, fuel, oil, those close so you don't supply fuel to the fire. These close so that that engine, where there's smoke isn't going up into the airplane. And so rather than saying, okay, you've got to activate the fire system, and then you got to close the bleed valve, and then you got to shut off the fuel, you know, you got to close the firewall fuel valve, and then you got to close. No, when you hit that, it does everything. It seals that engine off. And this is one of the items that'll be controlled by that through this same kind of control computer and logic. Okay. So this feeds into user systems. Who uses bleed air, or what uses bleed air? What are some of the items that you would think of on the aircraft that are going to use bleed air, use pneumatic, or users of the pneumatic system? Anti-ice, thrust reverser. What else? What's that? Fog protection, part of anti-ice and rain protection. What? Door sealing. That was in your report, wasn't it? Yeah. Pressurization, door seal pressurization, that's part of it. But a lot of the doors have seals that inflate. Okay, so you close the door and then you want to get a good seal. When you pressurize, when you turn this on, the seals inflate and squeeze, fill that gap between the door and the fuselage. Okay. Air conditioning, heat, environmental control. So you can see there's a lot of things. Engine starting is part of this. These turbofan engines, they use air turbine starters rather than electric starters, so you need pneumatic for that. Hydraulics. What is it used for in hydraulics? When we talked about hydraulics, where did pneumatics come into play? It can run pumps. There can be pneumatically driven pumps. What else? What? Scavenge pumps more fuel system. Right there you got fuel. It can run, you know, sometimes it can run fuel type pumps. Or pressurize the fuel tanks to help push fuel. An airlock for like a pressure. I don't know that anything's really a pneumatic lock because air is still compressible. You know, even if it's pressurized, it's still compressible. Hydraulics, a big one is reservoir pressurization. Remember we talked about the reservoirs being pressurized to prevent foaming and to help push that fluid to the pumps that are maybe not self-priming. Oh look, I've got thrust reversers twice. I've probably had this slide on here for 5 years. It's been there. Potable water, okay? Pressurizing water tanks to force water to the sink, to the coffee maker. And then vacuum waste systems. You run that air through a venturi, it creates a vacuum, and you can suck the poop away. Some others, now into sources. Getting our engines, our APU, and then we worked with a ground air cart start when we did the lab, a huffer cart. They can also be bottle carts. We had one of these at the first airline I worked for, a little Podunk Airport, northern Wisconsin. A bottle cart is a giant air bottle that you get like 1 or 2 engine starts out of, and then it's done. It's got a little shop air compressor on it that has to sit there and pop, 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 pop to refill it. It takes like 7 or 8 hours to refill the bottle. It's used. So we had it, and it was, first of all, it was never pressurized when we actually needed it to be because someone forgot to plug in the little compressor. And second, it seemed like our pilots, anytime they did a start with one of these, they forgot how to start the engines, and they would end up misstarting. And if the bottle did have pressure, they would end up using all the air in the bottle, and then they wouldn't have running engines, and they'd sit there for another 6 to 8 hours to repressurize the cart. But one of the issues with bleed air from any of these locations, particularly the engines or the APU, is that it's a very expensive form of energy to use on the aircraft. And by expensive, I mean when you turn on bleed air, if you are operating an engine or if you're operating the APU and you open that valve and begin to use bleed air, you turn on your packs, or you turn on wing anti-ice, you can see a significant increase in fuel burn, as well as typically an increase in exhaust gas temp or inner turbine temperature. Okay. And so what that means is it's going to use a lot of fuel. You get reduced thrust. A lot of these systems, when you move the throttles to full power setting for takeoff, it actually shuts off portions of the bleed air system for that period of time where you're at real high power. It increases the heat in the engine. So that cost, it's not just the fuel burn, but it's also the fact that anytime you're running that engine with a higher and increased heat, you're putting more wear and tear on the components inside. And so it's going to reduce the lifespan of some of those components inside. Hence the wear and tear at the bottom. Okay. So what have airplanes, or what have manufacturers and engineers done to fix this, or to rectify that? They get rid of it. Where'd they get rid of it? What? The 787 is a no-bleed architecture aircraft. It is all electrical. The wing leading edges are electrical. Even the packs that still run on compressed air, when we talk about the pneumatic packs, rather than taking bleed air from the engines, they use electricity to drive a compressor that feeds air into the packs in order to, kind of like what our mock-up board does over in the lab. We run electricity to run a compressor. That's where we get that warm bleed air, and then we run that through an air cycle machine to cool it down and get cold air. Okay. It has to, because that's what they did. That's how they got some of the efficiencies of it, is by going away from bleed air. So yeah, so it's in that case, it's more efficient to run a bigger generator. And part of that is they run a generator at a higher voltage as well, right? So rather than the typical 120 volt, that airplane has, I think, a 277 volt system or something like that. I mean, it's got some real, or even like a 400 volt system. It runs at a higher voltage, so you don't need as much current to get the same amount of work out of it. So we have to be able to control this. On the aircraft that do use this, we've got different control methods. And so these are things like shut-off valves, which are simple on-off. They're typically open, fully open or fully closed. Okay. They can be operated different ways. Things like solenoids are electric. They can use the air pressure itself in the system to pneumatically operate. They can be motor driven. So a motor versus a solenoid. A motor is a physical, like, gear motor turning thing. The solenoid still uses a diaphragm type device inside of it. They can be check valves, which are typically spring-loaded closed, and pneumatically operated. How are they pneumatically operated? Air just pushes against them, they pop open, right? We can have load control or pressure regulating valves. Often they're combined with a shutoff valve. Okay. And then things like combination valves is what I was talking about there. Pressure regulating shutoff valve, load control shutoff valve. So it works as a shutoff valve and it does some kind of a regulation. So what do these look like? Here is a load control pressure regulating valve. So in this case, what we have is, here is our duct, and we've got to be able to turn it on and off. We take a little bit of pressure from the pressurized side, and we run it up against a diaphragm. And that diaphragm has spring pressure on it. And now what that's going to do is, as that diaphragm moves, it's going to turn this little torque shaft, and that's going to open and close a butterfly valve. Now, if you just ran the pressure here, it would push this open all the time, right? It would always push it one direction. Maybe pushes it open, maybe pushes it closed. I shouldn't say it opens it all the time. Some of these fail closed, some of them fail open. When you shut off the pressure, some of them automatically go closed, some go open. It just depends on the design. But what happens is some of the pressure comes here, and it goes to what's called a torque motor controller. And that can do a couple things. One is it can bleed off pressure in this area, which will allow that spring, allow that plate to move. The other part is it can add some air to this side, which will increase or decrease the spring pressure here, okay? And so we can use essentially one of these little devices in order to control that valve. So it's still operated pneumatically, but it is controlled electronically. And essentially what this is doing is here's that high stage air coming in, and it's got this something called a little torque motor. And if it's, if the torque motor, this is basically an electromagnet type, little electromagnet kind of flapper valve thing. If it's pushed over this way, it's going to kind of close this off, and you're going to get ambient pressure going to your high stage bleed, right? It's going to reduce the pressure on the going back to the right side of that valve. It's going to reduce the pressure coming back here. If we open this flapper is going to come across, it's going to block off the ambient pressure, and now that high pressure is going to go down, and going to go, oh, there we go. That's the slide I'm looking for. They should be more above each other. But we move this over to the right. This torque motor end moves to the right. High pressure air can flow through here, and then it's going to come back down the right side of the actuator, push on this, move it to the left, and you can see that's going to have some valve control. So we can use those differential pressures to push that valve control piston left and right and be able to open and close the valve using an electronic signal, but not an electric motor. These are very low current. The electric signal coming here, they're just little tiny electromagnetic things. So they don't use a lot of current. Okay? We don't need to run big, heavy-duty wires to run some kind of an electric motor to push the valves open and close. Okay? So you can, that goes there, that can go back and forth there. And this thing can move left and right in order to operate it. Okay. And so those can be, like I said, they can be purely a shutoff valve. They can be either in the closed or open position, or they can be some kind of a regulating shutoff valve, whether it's pressure or flow regulating. They can vary, this butterfly valve in the middle, rather than being one that's purely open or closed, it can go halfway, or it can go 3/4, or it can go left. So you can provide regulation as well. With all of these, we've got hot air traveling through the airplane. We want to make sure that we don't have any leaks anywhere that could potentially cause damage. And so in these systems, we have bleed leak detection or overheat detection systems. So these can kind of be looped in with or contained in fire protection, fire and overheat protection, but they're also kind of part of this system as well. Because these are loops or spot detectors that are similar to what we'll see in fire protection systems, but they activate at a much lower temperature. Right? They're going to activate at the air temperatures that we would expect to see in the ductwork, 300 or 400 degrees, versus the fire temperatures that we might see of 1,000 degrees. And again, this one shows ones that are loop type. They run along the sides of the ducts. Similar to, you've seen Kitty and Fenwal type loops. They can be coaxial, which is like a Fenwal dual element, is like a Kitty. Is everyone familiar with that? We'll look at them in next week when we do fire protection. But they run alongside the ducts. Now, what do you see a problem in that? If they run along one side of the ducts, what kind of a problem does that potentially cause? If you're trying to find leaks in the ductwork and they run along one side, doesn't cover the circumference. What if we get a leak in the top and it's going this way? So what these ducts are is they're not actually just a single tube. They are an inner, they have two tubes, one inside of the other, oftentimes. The tube on the inside is the higher pressure tube that's designed to contain the air normally. The tube around the outside actually has little holes in it. And those holes are on the same side as where the loops are run. So if that inner tube leaks, it goes into that space between the inner and the outer tube, and then it'll come out where those holes have been intentionally drilled, which is pointed at the duct or at the loops. Or spot sensors. If we don't have loops, if we use spot sensors, which are like switches, those are just one spot. Those would be right near those holes. The other spot they'll be used is near any kind of a joint. And most of these use V-band clamp style joints. So I know in engines, when you've done the starter stuff, you've used the V-band clamp to hold the starter on the engines. Many of you have seen those, or you've at least seen groups working with them. All these ducts have flanges on the end of them that kind of butt together, and then the V-band clamp comes over and holds those flanges together. There's typically no seals in them. It's typically a metal-on-metal seal. They don't have, most of them don't have O-rings in there because, again, these are hitting 400 degrees sometimes. So it's a little bit warm to put an O-ring in there. But they're that metal-to-metal seal, when you take those two, and they're relatively flat. They're not super high precision machined or anything, but when you take, they're actually a flange that's kind of bent over like this. And they come together, and with the V-band clamp over, it forces those flanges to kind of squeeze together really tight. There are, when you go in the manual, there are limits. You can actually have a very small amount of leaking on these. It'll say you can have some generalized leaking on the ductwork. Not too much, but a little bit sometimes. Okay. And then those are going to feed in, these looped elements, these spot sensors, they're going to feed into some kind of a monitoring system computer. And that computer can be either, and oftentimes it's the same computer that's controlling the whole bleed system. The other configuration is it could feed into like a fire and overheat control computer, but that talks to the bleed control system. And so if a leak is detected, it can automatically close those shutoff valves or isolation valves or things like that. On newer aircraft. On older aircraft, you get warnings, cautions, and you as the operator would have to deal with it. Newer aircraft, it does it. It gives you the caution. It tells you, hey, something's up. But it can oftentimes close valves, close isolation valves, close shutoff valves before you even have a chance to react. Question? If you have a leak, it's the hot air that would be blowing out and hitting the sensors. Well, like this shows a loop style one running along the ductwork. Sometimes they have spot sensors. So they're, say, remember I said there's holes along here, right? Maybe there's a spot sensor and a spot sensor and a spot sensor at the joint, and another spot sensor and another spot sensor. There would be several. There wouldn't just be one spot sensor. They would be in several locations along the ducts. Okay. That tends to be older aircraft. Most newer aircraft use the loops like that provide a continuous length. But again, they can't monitor 360 degrees around the duct, so that's where it's important that you have that coaxial duct, the inner duct and an outer kind of containment duct that would direct any leaking air towards the loop so that you can pick up that there's a leak. So now all this system, we've looked at this system, now we're going to start looking at some of the users of it. Now we talked about ice and rain protection in an earlier lecture. We're looking today at the environmental control system. And so now we move out of ATA Chapter 35, and now we move into ATA Chapter 21, which provides us environmental control and then gets into pressurization and that kind of thing. So the environmental control makeup is we have our packs, which provide heating and cooling. You can see those on this diagram. There's a left and a right pack. These systems typically are going to have some kind of filtration. Now, the air coming from the engines rarely gets filtered. Okay, there's really not much in it. We're up at 30,000 feet. There's not much in the air, maybe a little bit of dust. Okay, but what part of the engine's it coming off of? Where are we getting the bleed air from? It's coming off the compressor, right? It could be stage 5, 6, 7, depends on the engine. You know? Okay, so it's coming off the compressor, so there is no, don't make the mistake of thinking it comes off after fuel is added. Right? Sometimes I get students that say, "Oh, it comes off, it's the combustion set." Well, no, you wouldn't want to take a bunch of combustion gas and route it into the airplane. You give everyone carbon monoxide poisoning. Okay, so it's coming off the compressor. It's before it gets to the combustion chamber, before fuel's ever added or anything like that. The heat purely comes from the compression. Okay, taking that air and squeezing it and squeezing it and squeezing it in the compressor, that's where we get the 400 or 500 degree air that we need for these systems. So the filtration is really more of a recirculation thing. That is, we take air and move it around the cabin. And as it moves around the cabin, it picks up bits of hair and skin cells and bacteria and virus particles. Someone flushes the toilet, right? And the plume of bacteria and virus particles go in the air, right? So there's filtration. Most airplanes, there's a few I worked on that didn't have it, by the way. They just recirculated everything. Yummy. Airplanes are gross inside. People are gross. Passengers are gross. Just get that out there. Okay. I loved working on the airplanes. I hated doing anything that involved dealing with the people side of it. If I could just work on cargo's my thing, I think, ultimately. Circulation, then we want to move that air around in the cabin, the cockpit. We need to keep the avionics cool. And the cargo compartments are included in here. Right? Has anyone ever flown with a family pet? Taking your dog anywhere? I don't recommend it. You have? So where does the dog go? Were you able to bring it in the cabin with you? It was a German Shepherd, too big. So they go down in the cargo compartment. So the cargo compartments, everyone's laughing. The cargo compartments are rated, most of them are rated for live animals. Okay, so they have to be temperature controlled. They have to be pressurized. They have to have a certain amount of air turnover, everything else. Now, if there's a fire in the cargo compartment, that thing's sealing off, they're dumping halon in there, and your dog is not going to make it out. Okay, just be aware of that. And the rampers the baggage handlers that deal with this, we won't even talk about the rampers in Orlando, that they were flying, a dog had just won Best in Show at the American Kennel Club Association dog show. And the baggage handlers decided they wanted to see what this dog was that is worth millions of dollars now. So of course they opened the cage and the dog bolted on the Orlando airport. They never caught it. They never found it. Anyone have been to Orlando Airport? What is Orlando Airport? It is a swamp. What is in swamps in Florida? Alligators. So I would not recommend it. If you're going to fly with your pet, do it air cargo versus baggage. It might go on the same plane, but they're treated much better. You take them to the cargo terminal, not to drop them off and then, I don't know why they did, but yeah. There are airlines, you can't, but you could send air cargo. There's a company that operates 727s called Equine Air. Their bread and butter is moving around Saudi horses. Yep, they take polo teams around and stuff. So, but they're up in the main. They've taken out the seat. They're like the 727 we got, and they've got horse stalls on the main deck. So yes, animals are terrible for corrosion. We got a 4-year-old plane back from Vietnam where they'd been bringing chickens on board, and it was more corroded than some of our 15-year-old airplanes because they were allowed to just bring them, farmers could just bring them in the cabin with them. You got to bring your chickens to market. You bring a cage full of chickens in the cabin. This plane was disgusting. But so the bleed air feeds into the environmental control system. And here is a full overview of a pretty typical environmental control system that we have here. Okay? Pretty simple, right? Nothing going on here. Okay? Here's our aircraft. We've got flight deck, forward and aft cabin areas. Here's our outflow valve. Okay? Shows how all the ductwork's connected. We've got a couple packs over here, the cooling air for the packs. So here's our flow control valve. So this here on the left is coming from the pneumatic manifold. So this is essentially everything shown here is getting into environmental control. This is chapter 21 now. And the key component in here, one of the key components we're going to look at is the cooling pack. Okay? The cooling pack is made up of, at its simplest form, is made up of a couple heat exchangers. It's made up of a compressor and at least one turbine. This one's a dual turbine design, and then some way to remove the heat, some overboard heat, and then we've got to have a way then to basically mix the air back together in order to send it out. Here's our hot air. We have hot air coming in here. That bypasses everything. We have cold air coming out of this expansion turbine, and they mix together to go to the cabin. They go into the rest of the system where they're going to ultimately go to the cabin and the cargo bay and everything else. So off they go to that side. Okay. So the various systems that make that up. Now, when we're working with these things, we got to understand that there are limitations to what we can do. So with our ECS supply over time, we're going to get different temperatures. So during climb, those engines are working really hard. The air coming out of the engines here on this particular airplane is somewhere around 550 degrees Fahrenheit. Okay. And then during cruise, you can see it sitting just above 400. And depending on altitude, you get a little bit of a variation because the temperature of the air is going to change coming in. The compressor is going to heat it up, but it's, if your air starts here, it'll end up here. If your air temperature starts here, it's going to end up here. Right? The higher you go, So average air temperature supplied during flight. And then you can see here, if we go into descent, you get a big drop, right? The engines aren't working as hard. They're going a lot slower. They're not compressing air as much. And so, we'll get these our systems on the aircraft. Environmental control, we already talked about ice and rain protection. They are going to have to deal with these different temperatures. So the way they do that is many engines, and you've seen this already, are going to actually pull air from different sources on the engine. So there's a high pressure. This would be like we saw, what was it, 6th and 10th stage on the AT9 that we had to identify, or 8th stage, 5th and 8th, 8th and 15th, 8th and 15th stage, that's it. Every airplane I've worked on that's from different stages, so trying to remember which one's which is. So 8th and 15th stage. So high pressure air would be like the 15th stage air. Low pressure air would be like the 8th stage air. But ultimately, this is where I've talked about with a lot of people, is ultimately the regulated manifold pressure on this aircraft is 45. So we want to have at least 45 PSI. Well, ground idle, we don't even get that much. Flight idle, we're right at it. It's designed to be at that flight idle level to get the minimum PSI. So anywhere from ground idle, flight idle, up to like kind of the mid power between flight idle and max power, we're running off our high pressure bleed. Okay? High pressure shutoff valve is regulating the pressure. In this case, when you get about halfway between flight idle and takeoff, you can see it starts to mix because now our low pressure is getting high enough that we can switch over to using low pressure. Rather than having to regulate our high pressure way down, we can just regulate that low pressure a little bit. So it switches over, and I don't even remember what this acronym is. That's a really long one. Too many letters to remember, too many words. But essentially the high pressure valve starts to close, and the low pressure starts to take over as our bleed source in order to supply that 45 PSI that we're looking for up at the aircraft. And so that 45 PSI is going to go into our ECS pack. And as I mentioned a minute ago, it's made up of an air cycle machine, which the air cycle machine itself is a turbine driving a compressor, and it's also known as an expansion turbine driving a compressor. typically 2 or more heat exchangers, often called the primary and secondary heat exchanger, which are cooled by, in the air when the plane's flying, they're typically cooled by ram air, but on the ground, they're going to have some method of forcing cooling air over them. The 727, that uses electric fans. There's electric fans that came on. Other aircraft, this expansion turbine not only drives the compressor, but it'll also drive a fan that can do it. So it's a mechanically driven fan, but one way or another, there's some kind of a fan that's typically used to run cooling air over those heat exchangers so that energy, that heat energy, can be dumped overboard. And then we got to mix hot air and cold air back together in order to get temperate air for our cabin. So that's done by things like dual bypass valves, mixing valves, and then some kind of a manifold. To control all this and monitor it, you're going to have various pressure and temperature sensors in quite a few different areas, especially new aircraft. They are all over the place in there. They've got turbine inlet and outlet temperature and pressure, compressor inlet and outlet temperature and pressure, heat exchanger, primary heat exchanger in and out temperature, secondary heat exchanger in and out temperature. You know, they've got all kinds of stuff. Older airplanes may have quite a bit fewer sensors. Newer ones have a lot. They're not all shown at ICAS at the same time. But what's really neat for maintenance is often you can go into a maintenance mode on ICAS and you can pull up the entire list of all these things for troubleshooting. Makes life much, much easier. Or more complicated if you get confused if you don't understand the system and you start looking at all these numbers and you don't know what's going on. Sometimes it's nice, you get the schematic drawing in front of you and start like, okay, here's this temperature and here's this pressure and and do they make sense, right? You know, and then they're going to be automatically and manually controlled. They're going to have provisions for that. And automatic control nowadays is done by a computer. So we'll go ahead and take our first 10-minute break.